Welcome back to the channel. You know, when we look at 2D arrays or matrices, they often look intimidating, right? It's just a grid of numbers. But in an interview, that grid can become a maze. How do you find a number efficiently? How do you spiral your way to the center without getting lost? Or the hardest one, how do you calculate the sum of every possible submatrix without your code timing out? Hello everyone, I am Supratim, your coach here at Techmine Guru. Today, we are diving into data structures and algorithm lecture 15. We are focusing on advanced arrays. Specifically, we are tackling two-dimensional arrays, search, traversal, and optimization. So here is our agenda for today. First, the search, navigating a sorted matrix, right? Then the boundary, where we will walk around the perimeters. Third, the spiral invert traversal, the spiral matrix. And finally, the insight, where we will find the sum of all possible submatrix using pure math logic. So let's get straight into it. So let's look at our problem one, the sorted search. The task is to find an element k in a matrix that is both row-wise and column-wise sorted, right? Now looking at the matrix, you see the numbers are increasing as you go right and as you go down. The numbers are increasing in both the directions. The intuitive way is a brute force approach where you can check every single element, but that gives a time complexity of O of n cross m. So our goal is to do something better than that. So suppose the target is 8, right? We have to find this 8 in our row-wise and column-wise sorted matrix. So here comes the staircase strategy. Instead of searching blindly, we start at a specific spot. Say we start at this top right corner, which will be 0, m minus 1. So here is the logic. If the element we are sitting on is greater than our target element, we know k cannot be in that column, right? If the element are sitting on is greater than our target k, we know k cannot be in that column because everything below is even bigger. So we move left to decrease the value. So for decreasing, we will move left to decrease the value. However, if the element is lesser than k, we know k isn't in that row. So we move down to increase the value, right? So you just have to remember this logic that you have to start from the top right 0, m minus 1. If the element is greater than k, then we know that k cannot be in that column because everything below is even bigger, right? And we move left to decrease the value. Similarly, if the element is lesser than k, we know k isn't in that row, so we move down to increase the value. Let's look at the code. So we start from the top right. That's why we kept I is equal to 0 and j is equal to n minus 1. Now we are running a while loop where we are checking the boundary condition as I should be lesser than n and j should be greater than 0. Since we are starting from top right corner and moving towards the left, so that is why j should be greater than 0. So if we found that element is equal to k, we will return true, or else if we found that the element is greater than k, we will move left. So for moving left, since we will move along the columns only, that's why our j will decrease. And if the element is lesser than k, we will move down. And for moving down, see, we move on the rows, which is increasing in the down. So that's why we did else I plus plus. So why is this powerful? Because in the worst case also, we traverse just one row and one column. This brings our time complexity down from O of n cross m to O of n plus m. That is much faster than checking every cell. And what will be our space complexity? Since we are not taking any extra space, so our space complexity will be O of 1 only, right? So this is also a LeetCode problem. So I have mentioned the link in the description as well. Now let's move on to the next question, which is the boundary traverse, where we will traverse over the perimeter in clockwise fashion from here to here, then from here to here, right? But when we want to walk the edges, there is a trap here. If you aren't careful, you will print the corner twice, one while going from here and one while coming down to here. And similarly, this will hold true for the complete perimeter. So how do we solve this? We can solve this using for loop breakdown technique. So when we are traveling in the first row, then our columns will change, right? So our loop 1 will just iterate from column 0 to n minus 2. We will just stop before the corner element. Now in the loop 2, we will start from the last column, but always from the first row, right? So in this, while moving down, our column will always remain n minus 1 only, and our row will increase from 0 to n minus 2. Again, we are stopping one element before the corner, so that when we start the third loop, which will be from the last n minus 1th row, we will start from our column n minus 1 and we will move till the first element, not till the last. Again, we are not moving towards the corner, because in the loop 4, we will again move from row n minus 1 to 1. So that will cover this corner element. So in the loop 3, since we are moving from n minus 1 to 1, our j will decrease here. And similarly for the loop 2 also, here since row was going down, I will increase here, right? In the loop 1, since we are moving from left to right, j will increase here. And similarly in the last loop, where we are iterating from row n minus 1 to 1, our I will decrease here, right? So let's come back to the code. We have initialized I is equal to 0 and j is equal to 0. So this for loop will just print first row from left to right. Since we are moving along the first row, which will be in column only, so our columns will increase, j plus plus will be there. Similarly, for the last column, which will be this one, from top to down, we will again start a loop from for k is equal to 0 to n minus 2. And here, since we are moving down, so our rows will increase, right? So we just ran a loop from for k is equal to 0 to n minus 2, and we just increased in our row, which is I plus plus. Similarly, for the last row, since we are moving from n minus 1 to 1th column for printing the last row, that's why our j will decrease since we are moving from right to left. And lastly, printing from bottom to top, this column, our I will decrease, right? So here the for loop runs from k is equal to 0 to n minus 2, and here the I will decrease from n minus 1 to 1, right? So by successively printing these 4 for loops, we are successfully traversing over the boundary. So since every loop will have the time complexity as O of n, so what will be the total time complexity? O of 4n, which will be again O of n only. And since we are not taking any extra space, the space complexity remains the same, which is O of 1. Now let's take this boundary concept and level it up. Now let's solve a problem printing a matrix in spiral order. So you have to print the first boundary, then your wall will decrease, which will be the second boundary, like this, and lastly you will come up to the last one. So here you have to just use the boundary concept layer by layer. So the goal is to print every element layer by layer, spiralizing inwards. So here we will use the shrinking box strategy. Imagine walls closing in one matrix. So we define 4 pointers here: min row, max column, max row, and min column. And after every iteration, the box will decrease. So initially the box will be like this, again the box will be like this, and similarly we will proceed. So here is the simulation. Print the top wall, then increment min row to lock that row out. Then we will print the right wall and then decrement the max column. Then we will print the bottom row where we will decrement the max row. And then we will print the left wall, which is this one. And here we will increment the min column. So we repeat this process until our count of printed elements equals the total element. So let's look at the code. So our code starts with a while loop where we are checking while n is greater than 1 or not. And I have just copy pasted the boundary code here, which will print all the boundary elements of that specific matrix. So we will repeat this process until our count of printed elements equals the total elements. The code uses a while loop, n is greater than 1, and follows the same top, right, bottom, left pattern we just discussed. This touches every element once. So the complexity is effectively O of n cross m, or O of n square for a square matrix. So every time we print the boundary, we have to increase I by 1 and increase j by 1, so that it gets started from the next row. So first this boundary got printed, then this boundary is getting printed. Similarly, after that, we will print this boundary. But why we are decreasing n by 2? Because every time when we are shrinking the box, two walls are getting shrinked from both the sides. That's why n will always become lesser than 2 of the previous number. So that's why n is equal to n minus 2 has been kept here. And what if n is odd? So if n is odd, that means we will come out of this loop and we will have only last element left. And that we can check using this condition, where we have simply checked if n is equal to 1, we will print the last element. And this is not needed in the even case, because in the even, there will be no single element left. So this is also a LeetCode problem. The link I have mentioned in the description as well. Finally, we arrive at the toughest problem of the day today. Problem 4, sum of submatrices. So where we need to calculate the sum of every possible submatrix. You remember, right? In our previous lectures, we have calculated the sum of every possible subarrays. So we are going to do something like that. The task is to calculate the sum of every possible submatrix inside our grid. So if you try the brute force approach, iterating through every possible top left and bottom right coordinate, you are looking at time complexity O of n to the power 6, right? Why 10 to the power 6? Because you have to run one loop for traversing in row, then one loop for traversing in column. And that you have to do with the start index. And similarly, two for loops for the end index, where for the end index, you will traverse for row and column. And when you have the start and end index, you will simply run two loop more, where you will just sum up all the elements between those start and end index matrices, right? So the time complexity here will be O of n to the power 6, which is very, very slow. Even if we do prefix sum optimization here, it will be again O of n to the power 4. And at that time, the space complexity will be O of n square. So it will be still slow. But from the earlier lecture, where we needed to find the sum of every possible subarray, we used a technique called contribution technique, right? Which brought O(n) cube solution to O of n by simply using one formula. So let's see how we can use that contribution technique here. So we need a shift in perspective. So this is called contribution technique. So here you don't try to find all the matrices. Instead, pick a cell I, j and ask how many submatrices contains this specific cell. Similarly, how we used to check that how many subarrays that particular element can have. Similarly, for this also, we will do the same. So if we are able to find what is the possible start indexes and what is the possible end indexes, we will be able to apply our contribution formula. So the contribution formula will be same, which will be equal to value of I, j into number of matrices containing in it. So let's visualize how we can calculate the number of matrices containing in it. So if we have selected this as our I, j, so how many top left choices will be there for selecting this one? Means how many start indices will be there? So for selecting I plus 1, right? Because in one column, when we iterate through row, the I will increase, right? Similarly, when we iterate over the columns, then how many choices will be there for this j index? J plus 1, right? So our top left means start indices choice will be I plus 1 into j plus 1. So if we have reached till I, j, then how many bottom rows will be left? N minus 5, right? Similarly, how many right columns will be left? M minus j, right? So what will be the number of choices for selecting I, j as the n index? Will be n minus I into m minus j. So our total top left choices will be I plus 1 into j plus 1, and our total bottom right choices will be n minus I into m minus j. So our contribution formula comes up as summation of a of ij into, this is our top left choices and this is our bottom right choices, right? So we simply ran two loops, one for iterating over the rows and second for iterating over the columns. And here we are calculating top left using I plus 1 into j plus 1, and similarly we are calculating bottom right using n minus I into m minus j. So we have taken a sum is equal to 0, where we are summing up all the top left into bottom right into a of I, j. So with this formula, we are able to get top left into bottom right into A of I comma j, which is that element's value. So what is the time complexity here? O of n cross m, right? Since we are running two loops only, one for the row and one for the column. And since we are not taking any extra space, the space complexity is O of 1. So this is also a LeetCode problem. The link I have mentioned in the description as well. So let's summarize what we have mastered today. Searching in a row-wise sorted as well as column-wise sorted matrix. So where we use the staircase method, which brought our time complexity from O of n cross m to O of n plus m. Then we solved the boundary problem, where we simulated 4 for loops and our time complexity was O of 4n, which is again O of n only. And then we use this boundary problem concept into the problem of spiral matrix, where we use the concept of walls getting shrinked and used pointers, which brought our time complexity to O of n cross m. Finally, we came to our printing total sum of all possible submatrices, where we used our contribution method and which brought down our time complexity from O of n to the power 6 to O of n into m. Or if it is a square matrix, O of n square, right? Visualizing the path is the first step. Now you have mastered the grid today. In our next lecture, we are going to tackle advanced interview problems on arrays. So if this lecture helped you, please hit that like button and subscribe to Techmine Guru. With this, I am Supratim signing off for today. Till then, keep coding, keep optimizing, and keep learning.